Hello everyone and welcome to the Fast GC Technology Forum, organised by the Analytical Scientist and supported by Avantor, Leco, Peak Scientific and Shimadzu. My name is Rich Whitworth, I'm Content Director at the Analytical Scientist, and I'm delighted to host today's event, which features not one, not two, not three, but four experts, each offering words of wisdom, innovation updates and application notes to help you jumpstart your Fast GC journey towards increased throughput, productivity and cost effectiveness. I'll give you a quick reminder of the agenda. First, we'll have Tony Edge, Site Director for Production and Research and Development at Hichrom Avantor, who will provide a theoretical 101 and discuss the practical implications in his inimitable style. We also have Ed Connor, Product Manager at Peak Scientific, who will talk supply with you as you consider the switch from helium to hydrogen. We have Franz Kramp, Product Manager of GC at Shimadzu Europe, who will delve further into the practical aspects, sharing insight into the various essential steps, including a focus on the need for rapid detection. And then we'll have David Benanou, expert analytical researcher at Veolia, France, who will further explore the applicability of fast GC, as well as the need for sensitive, robust and fast mass spectrometry technology. At the end, after our four presentations, I'll host a live Q&A session. So you'll have years, frankly, many years of combined experience at your command. So I urge you all to use the opportunity and ask any questions you may have about the shift to Fast GC. You can submit questions at any time using the prompts on your screen. And if the question is specifically for one of our speakers, please make a note of that at the start of the question and I can direct it to the appropriate person. Okay, that's more than enough from me. I'd like to get this Fast GC forum properly underway by handing over to Tony. Tony, the floor is yours.
Hi, and welcome to today's seminar. My name's Tony Edge, and I'm the R&D production site leader for the Hichrom facility within Avantor Sciences. I'm really delighted to talk to you today about Fast GC and the impact that that's had in terms of chromatographic separations, but also giving an understanding of why we would want to use Fast GC. So let me just go through what I'll be talking to you about today. So I'm just going to go through a little bit of the background to the development of GC, and then this will move on to the Fast GC, why we need Fast GC. I'll then talk about some of the benefits of Fast GC, and also look at some of the considerations that need to be taken when running with Fast GC. And then finally look at some real life applications. And then from there, we'll move on to just doing a quick summary of the presentation overall. So when we look at GC, we really have to start looking at the work that was done by Anthony James and Archer Martin. They developed modern GC as we see it today, and this was done in the 1950s, 1952. I've got a picture of Archer Martin on the screen, primarily because he's one of only two chromatographers that has ever won a Nobel Prize for their research in separation science. And I think it's a testament to the skill of the individuals that not only was it GC, but also HPLC that Archer Martin is remembered. If we look at those early days and look at the types of columns that were utilized, they were very much based on glass and also stainless steel. So the glass tubes would typically be a centimeter, 2 centimeters in diameter, not particularly very long, incredibly fragile. And the number of times that the glass tubes were broken on installation is beyond the number to count, unfortunately. These tubes were then packed, whether it be glass or stainless steel, were packed then with a variety of different stationary phases. So typically it'd be some type of elastomeric stationary phase. This meant that because it was a packed media within the column, it generated issues with pressure drop. And also it meant that the column could not be too long. And in order to ensure that chromatographers could actually get an elution off the column, they required relatively high temperatures. By the 1956, 1957, Archer Martin and Marcel Golay suggested the use of capillaries. They hinted that because with gas chromatography, the diffusion rates were much faster than were observed in liquid chromatography, that actually it would be ideal for open tubular as long as capillaries were being used. And this led to the development of capillary GC. Those initial capillaries were made from drawn glass and then eventually drawn silica. And although the technology worked, the drawn silica was incredibly brittle. And it wasn't until the late 1970s when Benanou and Zerena developed the fused silica columns, which had an external coating of a polyamide. This was developed from the fiber optics community, and it proved incredibly effective. From there on, further research started to focus on development and creation of a range of stationary phases that could be coated onto these fused silica capillaries. And then beyond that, as gas chromatography became an established technology, more and more focus was put on not the column, but actually the injector and the detector. Okay, so we've described GC. What's fast GC? Well, fast GC is a technique that allows you to substantially reduce the analysis time, but it doesn't mean that you lose the resolution. And so therefore you can use this in order to increase throughput. And I'll give you some examples at the end of the seminar where you can see quite dramatic reductions in terms of the analysis time. Fast GC can be applied to relatively trivial separations, but it can also be applied to medium and high complexity mixture analysis as well. And as I suggested earlier, it does provide a substantial improvement in analysis time. So typically anywhere between a factor of 3 and 10 when compared against conventional capillary GC. And again, I will show applications towards the back end of this presentation that demonstrate this. So what do you need? It all sounds very exciting that we should be using fast GC, but what is actually needed in order to make this happen? In essence, it's relatively trivial. What you need is a shorter column with a smaller internal diameter or narrow bore. So typically we'd be looking at columns that are 5 to 10 meters in length. And if you compare that against a traditional 20, 30 meter length columns that we would use with traditional capillary GC, and when we're looking at the internal diameter or the diameter of the capillary, now we're looking at 100 or perhaps less than 100. And again, comparing that with wide bore and standard capillaries of 530, 320 microns, there's a substantial reduction. In order to better utilize the technology, it's also useful to have a very high heating temperature rate, and typically more than what we would find when we're using traditional gas chromatography. And because the analysis is so quick, we also need to have a look at a very fast detector as well. Initially, when researchers were looking at fast GC, they looked at coupling together oven technology with the column, and so they would have heating mantles attached to the column. And although this proved very effective in terms of the technology and demonstrating technology, it didn't prove very effective in terms of commercialization. And so now manufacturers are moving away from that basic concept to one which is more universally or can be more universally applied. So we're moved now to understanding some of the theory, and in particular understanding how we optimize our chromatography. There are 3 key components that we need to understand. The first is that we need to get a degree of retention of our compounds on the column, no matter what format that column is. The second is that we need a difference in retention time between the compounds that we're trying to separate. And then the third component is that we need to ensure that we have minimal dispersion on the column, so that actually, although we've got a difference in retention time, our peaks are nice and sharp, so we can fully separate the components. And this can be summarized by the chromatogram here, where we can see 2 peaks denoted by retention times TR1 and TR2, and we can define a resolution equation which is a function of the retention times and also the average of the peak widths. From here, we can actually take that self-same resolution equation and we can look to develop it so that it actually considers those three components that I discussed earlier. And so here we've now got what's referred to as the Purnell equation. The resolution is defined by an efficiency term, a selectivity term, and a retention factor. And what we can do is that we can plot the impact that each of these individual terms has on the resolution. So let's have a look at this graph on the right-hand side and see what is actually happening as we alter each of these different components. So we have alpha, N, and retention factor. So what we can now do is take that self-same resolution equation and convert it into what is referred to as the Purnell equation. And this looks at those three key components. And what those key components are efficiency, selectivity, and retention factor. In order to better understand these components, we can look at the graph on the right-hand side. And this looks at how the resolution varies with alpha, which is the selectivity, N, which is the efficiency, and K, which is the retention factor. If we look at varying just alpha, we can see that as we increase alpha over a range that is typically used or found in a chromatography system, we can see that the resolution initially doesn't increase as dramatically as with the other two parameters, but once we get over a certain amount, then absolutely alpha seems to be dominant. Second dominant is the efficiency. So as we increase the efficiency, in this case from 0 to 25,000 plates on a particular column, we can see that there is a gradual increase in the resolution of that chromatographic separation. The retention factor doesn't seem to be a good one to alter, because with this one we can clearly see that we've maxed out the resolution once we hit a certain point. However, this now comes down to some of the practicalities of gas chromatography, and in particular the fact that within gas chromatography, unlike other forms of chromatography, there are limited retention mechanisms, and I will go through some of the retention mechanisms in the next couple of slides. As a consequence, although alpha seems to be the best approach to use for optimizing the resolution, actually for GC, it really is efficiency. So really we need to be looking at ways in which we can optimize N. And one way of doing that is by reducing the column diameter. So let's now have a look at some of the interactions that we get with GC and get an understanding of why are they so limited. So there are three dominant modes of interaction that are used within a gas chromatography. So the first of which is referred to as dispersive interactions, or sometimes known as London dispersion forces, or sometimes even hydrophobic interactions. This is where we have an instantaneous dipole-induced dipole. And the diagram at the bottom clearly shows what's happening. So it results from a temporary charge imbalances that exist between electrons in a molecule. As they randomly move around the molecule, it creates this charge imbalance, and those charge imbalances give the potential for molecules to interact together just on a very temporary basis. This results in transient small amounts of positive and transient small amounts of negative charge, and those positive and negative delta charges can actually then end up attracting molecules together, and this is what's happening on the stationary phase. So this is one mode of interaction. There are two other modes that we can look at. One is dipole-dipole. So this is where we have a more permanent movement of the electrons around, and so in this case we can see with the iodine chlorine that we have a slight delta positive charge and slight delta minus charge associated with the electronic configuration for these particular molecules. This is a stronger force than the London dispersive forces. However, it's weaker than the next one I'm going to talk about, which is the hydrogen bonding. With hydrogen bonding, we are now starting to move towards an electrostatic attraction between two polar groups. And classically, this would happen with perhaps a hydrogen atom and an oxygen atom between two different molecules. These are strong forces and much stronger than the standard dipole-dipole interactions. However, these are the three types of forces that are very dominant within GC. And as a consequence of these only being three forces, using selectivity to drive a separation is perhaps not the best way. So what does that mean then in terms of overall selectivity for a typical gas chromatography range of columns? So here we've got a series of different columns ranging from low polarity to high polarity. And as we go through these, we can go through different structures on the surface that are coated onto those capillary GC columns. And we start off on the left-hand side with a kind of squalene type structure, moving to the bisphenol and increasing the amount of bisphenol with the percentage 5%, 10%, etc., relating to the amount of bisphenol that we've actually stuck on. And then as we're moving towards higher polarity columns, we then start moving to a PEG, a polyethylene glycol type column. So we said that it's efficiency that drives the separation in gas chromatography, and absolutely it is. And so in order to get a better understanding, we really need to understand some of the theory behind this. And this will also give us a better indication of the impact that the column diameter has. So in order to understand the theory, we really need to go to either Van Deemter or Golay. And we can have a look in this case as a modified Golay equation. We can see that as we plot H, which is a measure of the peak width relative to retention time, reduced plate height, if you want the technical term, versus the linear velocity, we can see that we get a classical sort of U-shaped curve. So at low flow rates, we are in a regime which is dominated by longitudinal diffusion. As we increase the flow rate, the longitudinal diffusion has less impact, and now we're having an impact due to equilibrium effects between molecules moving to and from the stationary phase. Reducing the diameter of the column reduces that impact, and in so doing so, we end up with narrower peaks. And we can see from this very simplistic model that actually going from a 320 down to 100 micron internal diameter capillary, we see quite a substantial reduction in terms of that peak width relative to retention time. And this is matched up by the experimental data where we can plot HETP, height equivalent theoretical plates, for a range of different column diameters. And so here we're looking at different lengths and different ID columns, so ranging from a 530 micron, 320, 250, and 150 micron. And we can see that as we reduce the diameter from an experimental perspective, we actually see an improvement in terms of the performance. So clearly there's a driver here for improving our chromatography separation by using narrow ID columns. But in order to move between different columns, we also need to be aware of the impact of something referred to as the phase ratio, which is simply a ratio of the column diameter divided by the film thickness. In order to ensure that we get the same elution of the compounds, we need to make sure that the phase ratio beta is kept consistent. And at the table at the bottom, we can see a range of different film thicknesses and column diameters. So typical film thicknesses that we might use on a GC column, and a typical sort of range of column diameters. Thus, if we want to take a couple of examples, if I wanted to keep the same elution order using a 0.25 or 250 micron column that has a 0.25 micron film thickness, then I could use a 0.18 or 180 micron column against a 0.18 micron film thickness, and that keeps the same phase ratio of 250. And I can look through this table to identify how to do that. And it's important that we maintain that in order to make sure that we get the same elution order. However, it's not just elution or that we need to consider, there are some other practical considerations as well. The reduction in internal diameter does mean that the injection volume has to be reduced as well. So there are different ways we can reduce the injection volume, but the typical way would be to increase the split ratio. And again, I'll give you some examples of this. We need to have a look at the film thickness. So having a thicker film on the coating of the capillary increases the dispersion, and so that makes our peaks wider, and we don't really want that. Fast GC is about nice sharp peaks, so in this case we'd actually want a thinner film to be used. I've already talked about the column length, and we can reduce the column length accordingly. As well as that, we need to have a look at the linear velocity of the gas. So although the flow rate may not alter, the linear velocity will increase, and we saw that from the experimental data previously, but I'll give some examples later. We also need to be very aware of practical considerations that perhaps using a larger column have little or less impact. So things like column installation become a lot more critical, and making sure that we get a good cut on the column and install that column correctly are very important. So once we've taken those considerations into being, then we also need to have a look at how to change the various temperature gradients, etc. And so again, we can use some standard formula in order to ensure that we get consistent chromatography. So in this case here, the new temperature gradient would be a ratio of the linear velocity of the gas, the phase ratios, and the length of the column. And timesing that by the initial gradient would enable us to ensure that we get a consistent separation. We also need to make sure that the whole time that the isothermal components are also the same. And again, we can use the equation highlighted above in order to do that. That's all well and good, but does it actually work? Well, let's take some examples. So here we've got a series of compounds looking at a chamomile analysis. Using a standard GC, we can see here that we're running at a 55-minute analysis compared to a 10-minute analysis time using fast GC. And looking at the critical parameters that we've altered, we can see that in terms of the oven program, the temperature ramp rate goes from 3 degrees C per minute up to 50 degrees C. We talked about faster temperature ramp rates earlier. The carrier gas flow rate in terms of the absolute volumetric flow rate has actually decreased, but the linear velocity will have increased. The split ratio has gone from 1 to 50 now to 1 to 250 when we're running with fast GC. And then looking at that all-important column diameter, we're reducing from 0.25 millimeters to 250 micron down to 100 micron. Subsequently, we've been able to reduce the film thickness and also the length of the column. This is just one example, but let's go through 2 or 3 more just to confirm what we're seeing. So here we've got separation of some fatty acid methyl esters on the Hichrom HI-10 FAST column. And so we've got a separation of 37 discrete compounds within 12.5 minutes. And again, the reason we can do this is because we're running on a very narrow ID column. In this case, we're looking at a 200 micron column. We can also look at separation of pesticides. So one area that GC is often used is in the separation of pesticides. And again, we can see that using this time a 100 micron column with a 0.1 micron, apologies, film thickness and 5 meter column, we can now get a separation in 4.5 minutes of 17 commonly found pesticides that would be used in the agrochemical industry. And then moving then to the final separation, which is looking at a series of fragrance allergens. And this is using the Hichrom HI-SE54 phase. And this is looking at 100 micron, 0.1 micron film thickness, 5 meter length column. And we can again see a very quick analysis of 1.8 minutes for 29 peaks. Incredible separations that really, when you look at it, change the way that GC should be done. And indeed, people are using this approach in order to optimize their separations. So with that, I'll just quickly summarize what we've talked about today. So we've gone through some of the background to development of gas chromatography, and then moved on to why we want to do fast GC. Looked at some of the benefits of fast GC, so specifically looking at the faster analysis time, as its name alludes to, but also looking then at the ability to maintain resolution and how we do that through use of very simple equations. And then finally, based on the understanding, we've been able to take that knowledge and apply it to 4 practical applications. I've demonstrated how we can now look at separating many tens of peaks in a few minutes. And with that, I'll conclude, and thank you very much indeed for your listening, and I hope you found it useful. Thank you.
Hello, and thank you for attending today's webinar. My name is Ed Connor, and I'm one of the product managers from Peak Scientific. And today I'm going to give a presentation that focuses more on the setup and considerations for gas supply to your GC for fast GC. So the first question that many of you may have is, why would you consider using a gas generator instead of a traditional gas supply such as a cylinder? Well, if we look at the 6 figures on this slide, these cover most of the reasons why gas generators can provide advantages over traditional gas supply methods. So first, if we consider convenience, generators provide gas on demand. You don't have to worry about changing or maintaining supply stocks or even monitoring your supply of gas. The generator will provide gas 24/7. And then when we look at the consistency of gas quality, if you use cylinders, you will from time to time encounter inconsistent purity from gas cylinders, whereas gas generators, because of the way that they produce gas using a repeatable method, they don't have the same issues with inconsistency of gas supply. And in addition to that, because the generator can remain connected to your GC, you're not having to break the connection between the gas supply and your GC, so you're not risking the introduction of impurities, as is the case every time you change out a cylinder. And as I just mentioned before, generators will run 24/7, so you don't have to worry about running out of gas. Then when we consider safety, this is probably one of the key reasons that many of Peak's customers invest in hydrogen generators. And really the benefits of generators are that they have an extremely low stored volume of gas and can still deliver enough gas to supply an entire laboratory. And so they offer a much safer and convenient supply of gas compared to cylinders. Then when we consider the environment, cylinders are normally brought by truck to your facility, and of course as they run out you'll require repeated deliveries, and a generator, once it is installed, will not need to leave your premises. And as with all of our products, Peak are always striving to improve the energy efficiency of our products, and this includes our hydrogen generators. Then when we consider economy, once a generator has been purchased, the ongoing cost of ownership is actually very low. If you consider our precision hydrogen trace products for carrier gas, they require just an annual filter change. So it's a really low ongoing cost of managing your gas supply compared to cylinders. And then finally, as we're in the midst of a pandemic and have been for some time, we're realizing that generators are actually improving lab safety, because customers are able to have independence from those repeated deliveries from third parties, and this ultimately means that they're able to protect their workforce from the risk of COVID transmission. Okay, so we've seen the benefits of gas generators. What are the key points that you should consider when selecting a generator? So the first thing, of course, is to look for a high quality gas generator. And when we're looking at supply for carrier gas, normally the recommendation is to choose a generator that's supplying 6 nines purity or higher for hydrogen carrier gas. And you should pay particular attention to the oxygen and moisture content of the gas, as these impurities can affect your analysis as well as things like column lifetime. And a hydrogen generator can supply both carrier and any detectors that require hydrogen for flame, such as FID detectors. And one other point to pay attention to is the certification that the generator manufacturer has on their products. At Peak we have CSA certification, which means that we go through stringent safety testing in addition to the standard safety tests associated with CE certification. Then you will also want to think about the capacity that you need. So at Peak we have a number of options for hydrogen generators, and they have a range of flow rates from 100 cc's right through to 1.2 litres per minute. It's often important to check what the maximum pressure requirement of your method will be, and if you're not 100% sure, you can actually use method conversion software. So there are some options to download online where you'll be able to check the flow and pressure of your method at maximum column temperature, for example. And then water quality. So deionized water quality is very important when it comes to hydrogen generation. Most generators producing hydrogen will require ASTM type 2 water or better. And it's really important to have good quality water, because this will ensure that the PEM cell, which produces hydrogen in the generator, will remain healthy. And by using good quality water and changing it frequently, you should ensure that your generator runs for a long period of time. And then when we look at the tubing that you use to supply to the generator, first of all, try to locate the generator close to the GC if possible. This will reduce the number of connections between your gas supply and your GC, meaning that you should be able to identify any leaks if they occur, but you should also reduce the number of leak points. Stainless steel tubing is recommended for GC supply with hydrogen, but copper can be used if you are unable to source stainless steel. One thing to watch out for is that copper can become brittle over time. And a very important point is to avoid using tubing that has previously been used to supply other gases such as helium. So if you are changing carrier gas from helium to hydrogen, please remember to use new tubing, because what can happen if you use old tubing, the hydrogen will actually strip away any impurities that can develop on the inside of the tubing, and you can end up with very high background or the requirement to change some of the components in your inlet or potentially even the column. And of course, once you've invested in a generator, you want to make sure that the supplier can also support you once you've bought it. And at Peak, we have invested heavily in our service capability and consider ourselves second to none when it comes to after-sales support for customers. So when we look specifically at our hydrogen trace generator, it produces 7 nines purity for carrier gas, but can also be used for flame gas. We have flow rates ranging from 250 cc's per minute through to 1.2 litres per minute, and we have up to 100 psi output pressure. The generator will provide an uninterrupted supply of consistently pure carrier gas, and when it's started up, the generator will perform a safety check as well as continually monitoring the internal and external pressure to make sure that there are no leaks. There's also minimal stored gas volume and a relatively low pressure operation if we compare it to cylinders. As I mentioned at the beginning of the presentation, the maintenance is an annual change of the deionizer cartridge, and we have both CE and CSA certification on all of our precision products. So when we look at the considerations for converting carrier gas, what should you look out for? So first, when we convert from helium to hydrogen, I'm sure many of you are aware that hydrogen offers the opportunity to run your analysis faster than helium or nitrogen, and the reason for this can be seen in the Van Diemter plot on the right hand side. So as we increase the speed of analysis, so the speed of the gas through the column or linear velocity, what this shows is that the vertical scale, which is the theoretical plate height, for hydrogen, the plate height does not increase at the same rate as for helium and nitrogen. And what this means is that you're actually able to get better separation despite running hydrogen at faster linear velocities. And so ultimately you can get better separation than the alternative carrier gases despite running your samples faster. Again, it's important to pay attention to inlet pressure and consider changing to a narrow bore column if you need to increase the head pressure on your inlet. Reducing the inner diameter of your column will not only reduce analysis time, but it could also improve your overall chromatography. And one other point to consider is that you should really check the elution order of your analytes once you do make the conversion, as some peaks may change position. So if you're using a non-MS detector, this would be particularly important. Now, if we look at the key steps of converting from helium to hydrogen, first of all, check that your method can actually be converted. So some of you may be using methods that do not allow alternative carrier gases, so this is very important to check as a first point. Then do a lot of research. It's important that you read up on the process of conversion and also any tips regarding what you can expect and what to look out for as you make the conversion to speed up the process as far as possible. I mentioned there are method conversion software options available. I would really recommend using these to check the method conditions when you switch to hydrogen. And if you're using GCMS, there may be some hardware changes recommended by your manufacturer, so do check what is recommended for your system. And it's also important to be realistic about the time required for the conversion. It may not be as straightforward as you think. Again, reading up on the potential pitfalls and ways to make the process as simple as possible will help. And finally, remember that if you have any SOPs or other literature associated with your method, that this will need to be updated. And we have an article which you can see the link to at the bottom, which gives you a step-by-step guide to converting carrier gas, which is available on the Peak Scientific website. So very quickly, as we don't have too much time today, I'd just like to give you an example of speeding up analysis by simply changing the carrier gas. And in this case, we were looking at a method called detailed hydrocarbon analysis, which uses a 100-meter column. So this is an oil and gas method, and we simply changed the carrier gas using the exact same setup, and were able to cut the analysis time from just over 2 hours down to 73 minutes when using hydrogen carrier gas. So it's a huge time saving, but of course you can run as fast as you like, but if you don't get the separation required, then the results are meaningless. And so of course we needed to check that all critical separations were achieved, which they were. And another aspect that we looked at was to check the different overall constituent makeup of the sample. And we found that there was no significant difference regardless of which carrier gas was used between the overall percentage constituents recovered. Now, if you would like to find out full details of this study and others that we have, they are available on the PEAK website. So that brings us to the end of the presentation. I did just mention the PEAK website, so please do look for any information on products. We do have application notes and user stories. We also have brochures, data sheets and videos about many of our products. So please have a look at www.peakscientific.com, and if you have any questions, then you can also contact us via the website. So thank you again for attending today's webinar. I hope it was informative, and if you do have any questions, please get in contact with the PEAK team. Goodbye.
Dear ladies and gentlemen, I welcome you to this short introduction to about FAST GC. On some practical examples, I will show you the method improvements leading to faster gas chromatography. Well, FAST GC is an optimization method, so several parameters can be optimized to reduce the GC running time, but finally the same number of peaks must be separated in a shorter time, therefore a surplus of peak resolution is needed. Then your benefits are you measure more samples per time and you get faster answers on urgent questions, maybe interesting in control of production processes. Often you get improved quantification limits, so fast GC optimization results in sharper peaks and often in better signal-to-noise ratios. You will also observe a better recovery of thermolabile components due to the shorter dwell time in the hot environment. Then finally, of course, the GC requires less runtime for sequence analysis. If you use fitting standby methods or automatic shutdown and restart functionality, the running cost can be significantly reduced. Okay, the chromatographic resolution. So the peak resolution defines the distance between two signals in a chromatogram. If it is below if R is below 1.5, you see the peak starts to overlap. If it is far below 1, the integration might not be accurate. So what parameters influence peak resolution? There we have to start with the sample injection system. That means with a good sample transfer on the column, we set the basis for the few further improvements. So best performance in this case is of course split injections. Other injection techniques are possible but might have restrictions. So of course the strongest mean for better peak resolution is the column choice. There especially the stationary phase and the film thickness have a big influence on peak resolution. If we have a surplus of peak resolution, then of course we can improve our temperature program. We can increase the initial temperature and also the temperature program gradient for faster chromatography by of course losing then our surplus of chromatographic resolution. The linear velocities of the carrier gas also accelerate chromatography, but here the type of the gas is important because this defines in what ranges we can improve our linear velocities. That means how fast we can increase the flow rate. And last not least, we need a fast responding detection system. If the detection system is too slow to record the sharper peaks properly, all of these optimizations are finally in vain. On a very simple chromatogram with separating the peaks A, B, and C from the solvent heptane, I would like to show how different parameters in gas chromatography influence the peak resolution. The following examples are made on a GC2030 with split injector and FID detector on a simple standard column RTX5, 30 meters, inner diameter 0.25 millimeter, film thickness 0.25 micrometer, means not a dedicated fast column, a normal GC column, and here we will see what is possible. We start with a helium linear velocity of 40 centimeters per second and a temperature program starting at 100 degrees with a temperature gradient of 10 degrees Celsius per minute up to 250 degrees. With these settings, you see we have a big surplus of peak resolution between the three peaks, and we have a chromatogram time at the moment from a little bit less than 6 minutes. Increasing the initial temperature shifts all peaks of the chromatogram to shorter retention times. And another benefit is the cool down time of the GC is decreased. That means generally the one time per sample is less. But some restrictions occur. This is not suitable for some sample injection techniques requiring a refocusing on the column at lower temperatures. For example, split injection, then we have to stick at the lower temperatures, and we can just use the temperature gradient. Okay, here's some examples. We had here the 100 degrees, 150 degrees, and 200 degrees initial temperatures, and we see at 200 degrees we have decreased from a little bit less than 6 minutes to below 2 minutes. But if you see here already, the peak resolution is now really close to an end. It's just enough to cover the long-term degradation of the column. That means we could really stop here. If this is sufficient, we can continue. For further optimizations, I would like to use the initial temperature 150 degrees because here we still have a big surplus of resolution remaining. Increasing the gradient of the temperature program is very helpful if you have sample components covering a big boiling point range. Then the gradient in your temperature program can be adjusted for separation of the low and the high boiling point range. However, some restrictions occur. The maximum linear heating rates of a GC are restricted. So beyond the specifications, the GC cannot heat faster anymore. In our case, we heat up to 250 degrees. And our maximum linear heating rate is 55 degrees Celsius per minute. So increasing the temperature gradient from 10 degrees to 30 to 50 degrees Celsius, we see with 50 degrees Celsius, we reduce from 6 minutes almost to the same time we achieve with the 200 degrees initial temperatures. That means far below 2 minutes. But here, different here is we still have a surplus of peak resolution that we can use for further improvements. So the next possible improvement is the increase of the linear velocity, in this case of the helium carrier gas. Here we shift all peaks in the chromatogram to shorter retention times. How much that depends on the boiling point of the components and the actual temperature of the oven. At low temperatures, high boiling point components move, of course, less. Other advantage is, even with low split ratios, we can achieve sufficient flow through the sample injection system for a better transfer on the column. But this has, of course, also a drawback. With high split ratios, we increase the gas consumption, and that must be observed. The usage of split saver functionalities of the GC can reduce then the running cost significantly. We increase the pressures. That means your system should be well maintained concerning leakages, because at higher pressures, even small leakages influence the precision of the system. And you have to keep in mind, because of the viscosity of helium, nitrogen, argon, the pressures increase much with temperature. That means at high oven temperatures, you can easily reach the maximum operation pressure of the GC, which is typically around 1000 kilopascal. Okay, with increasing the linear velocity from 40 over 80 to 120 seconds, you see we can improve our chromatogram time below 1 minute. But what you can also observe is our peak shapes are not very nice anymore. So that means the peaks are not as sharp as they should be. And the reason is here we have not adjusted the detection system so far. The response of a detection system of a gas chromatograph is defined by two parameters, the sampling frequency and the noise filter settings that is normally named filter time constant. Noise filtering is used by every GC for removing the high frequent part in the baseline in order to improve the signal to noise ratios. However, if our peaks become sharper and sharper, the filter must be adjusted, otherwise it works not as it should be. It does not only reduce the noise in the baseline, it might also affect our peaks. That we can see here in this example. We have here sharp peaks. If our noise filter is adjusted with a filter time constant of 4 milliseconds, it is still a very sharp peak. If we increase the filter time constant up to 200 milliseconds, you see the peak height goes less and it becomes broader, and finally it's completely filtered out of the baseline. So for this reason, the GC 2030 you can set the filter time constants in steps from 2000 to 2 milliseconds in order to build up even very sharp peaks, in combination, of course, with the sampling frequency up to 500 Hertz. Back to our example, let's look on the helium linear velocity of 100 centimeters per second. Here we see our peaks, not very nice. They have at 50% height, they have a peak width here of 1 second. And this is the result with a filter time constant of 200 milliseconds and sampling frequency 25 Hertz. If we improve now our filter time constant to 50 milliseconds, we see a big improvement. So the signal width at 50% height is now reduced to half a second, and accordingly our peak height doubles almost. And our resolution, because of the sharper peaks, is improved almost a factor 2. In this example, the sampling frequency 25 Hertz was already chosen very well. If we increase this to 50 Hertz, we see only a minor improvement. The peaks gets a little bit higher. You see here this little green tips. So it means the peaks are still fully symmetric and completely covered. So it means the sampling frequency there was no need to adjust it in this case. Okay, now with this result, we can go to further optimization, and we change to hydrogen as carrier gas. Hydrogen is, of course, the best carrier gas for gas chromatography. So it's the best choice. It has a similar diffusion factor than helium for this chromatographic separation, but its big advantage is the low viscosity. At room temperature, hydrogen is of course roughly has a factor 2 lower viscosity than helium, and the viscosity increases much less with temperature compared to helium or nitrogen. Then, of course, we have the running cost. The helium is a limited natural source and increasingly used. It cannot be produced by gas generators like you can do with hydrogen, and therefore we expect increasing helium prices in future. The big advantage, of course, of helium is the inertness of the noble gas. At high temperatures, hydrogen can react with your components, especially if they become contact to hot metal surfaces. Then some detectors, like helium ionization detectors, cannot be operated with hydrogen as carrier gas. Here you really stick to helium. And last not least, hydrogen is burnable, and mixtures of about 4% hydrogen and air can explode. And therefore, special safety precautions should be considered operating hydrogen as carrier gas. But especially with fast GC, we profit a lot from hydrogen because the chromatographic resolution with increasing linear velocities decreases less than with helium. This way, we can improve now our example from at the beginning 6 minutes now, less than half a minute chromatogram time, and we still have sufficient resolution for further improvements. That means if it is needed, even higher linear velocities could be used with hydrogen as carrier gas. Okay, most likely your sample in reality is not that easy, and what can be done if the resolution of 2 or more peaks in your chromatogram are not sufficient? Well, then you must find a better capillary column, and from the 4 possible parameters of a capillary column, only 2 are appropriate. Unfortunately, column length and film thickness are not appropriate parameters to optimize for fast GC, because both, of course, improve the peak resolution, but even more, they increase the chromatogram time, and that will not work. Stationary phase is, of course, the strongest way to optimize separation and peak resolution, but on stationary phases with different polarity, the elution order of your components might change. If this should be avoided, then the inner diameter is a strong tool to improve the peak resolution on a column with same stationary phase, and finally achieve a surplus of peak resolution. Reason is, with decreasing inner diameter, the Van Deemter curves flatten, and with small inner diameters, if you increase the linear velocities, you lose less peak resolution because of the performance of the column. Another advantage is with smaller inner diameter columns, you have less gas consumption, but there are of course some disadvantages. You need higher pressures for the operation, especially with higher linear velocities. Therefore, hydrogen becomes preferred carrier gas in smaller inner diameter columns, and you operate typically with shorter columns. That means less than 30 meters, and with ID 0.1 millimeter columns, even less than 15 meters. The next point is smaller inner diameter columns have less capacity. That means the injected amount of the column must be reduced. Typically, you have to operate with higher split ratios. What you can do at the end of my presentation, I would like to show one example, what can be done with, let's say, in ultra-fast GC optimization. We have here a separation of frames with conventional GCs, 30 meter ID 0.25 millimeter Vox column. And we see we have here a chromatogram time for more than 30 minutes, and optimized on a fast GC RTX Vox column with inner diameter 0.1 millimeter and a length of 10. We can reduce this to less than 2 minutes with, let's say, still a very good chromatographic separation. Then I thank you very much for your attention. More information, if you are interested about fast GC, you can download our fast GC GCMS application book. I thank you very much again for your attention, and goodbye.
Good morning, ladies and gentlemen. I hope that in spite of the health circumstances, you are all in good health, and that you will enjoy the vacation period that is coming soon. I would like to thank the analytical scientists for the opportunity to present the results of this study. It is my pleasure to present to you today fast GC and hydrogen carrier gas, a method transfer story, or the way to learn why it is important when switching to hydrogen carrier gas. Learn about the base instrumentation, the base column, calculation, safety, cost, and more. I divided my presentation into 3 parts. Firstly, the fast GC, a short introduction, helium versus hydrogen, and the performance benefit. We will talk briefly about the safety, the cost, and the instrumental setup. Then, we will enter directly in the method transfer process, the calculation, the chromatographic optimization, and by the end, the resolution versus speed. And we'll finish by the mass spectral performance, which kind of MS, the ion source design. We will talk about the spectral quality, as well as robustness and quantification. Let's go back for a while to the basics regarding the Van Ditner's curves. Operating in the optimal plate height, this is a blue shade, region allows the best chromatographic resolution and efficiency to be achieved. By using helium, transfer to narrower ID column can enable some speed benefits while maintaining the resolution. But using hydrogen widens this operational range, allowing additional speed to be achieved with less compromise on resolution too. What are the practical considerations for your lab, helium or hydrogen? Regarding the safety, switching to hydrogen allows better analysis throughput to be achieved. But it is safe? We can say yes. The cost. Will it cost a lot to set up faster GC? How will my running costs be affected? It will be affected positively. Regarding the instrument suitability, do I need to adapt my GC or MS instrument to be compatible with hydrogen or to use smaller ID column? Small adaptation will be necessary. Regarding the safety, yes, we are going to banish cylinder from labs and from gas room. In this case, we have to use a generator, and I push you to use generator. Of course, hydrogen is potentially explosive in air at a concentration ranging from 4 to 74%, but from a point of view, to reach such level, it's a real challenge, whether impossible. With the EPC, electronic flow regulation, any leakage will shut down the carrier gas flow automatically. It means that the system will be in standby mode. You can introduce the split line in a fume hood or outlet of the lab, but sometimes leaks may occur at the end of the column or when the column breaks far from the inlet. So in this case, EPC will not stop. So it's possible to add inside your oven an hydrogen sensors with alarm and event option. The price of helium is increasing considerably from year to year. Thus, the USA, with the Stewardship Act signed by the Barack Obama president, is going to reduce the export of helium. And although important deposits of this noble gas have been discovered in Tanzania, the price keeps increasing. So, depending on if you are using helium or hydrogen and also the flow rate and temperature range you want to use, you may need an inlet capable of operating at higher pressure, like 150 psi. Hydrogen generators need an upfront investment, of course, including for water purification and possibly gas sensor too. Once implemented, hydrogen generators have a very low running cost, and you have very rapidly the return on investment. Regarding the GC column and consumable, they are typically in the same range, cost range, as those used for the normal speed GC. Regarding the instrument, some instrument needs parts to be adapted to use hydrogen. Instrument gas connection, tubing, rose pump, ion source component. The MS detector needs vacuum pumping capacity and efficiency to be able to operate with reduced vacuum pressure associated with hydrogen. The MS ion source design is an important factor due to the constant scrubbing effect on hydrogen. Considering the method transfer process, it is hard? No, it's easy. It is rather easy to switch from a method with helium as carrier gas to a method using hydrogen. You could reason empirically or apply a design of experiment. Although it sounds fascinating, but it will take a lot of time. Our recipe is to use Restex freeware, a ZGC method translator, and after about 10 injections, we can have an operational method in fast GC. I will show you the synoptic of our philosophy that allows us a fast and efficient method with high-speed GCMS. The reference remains your basic method with helium. In this case, for the basic method, we use a 30 meters column with 0.25 millimeters. And for the second experiment, you use a shorter column, 20 meter and 0.18 millimeter as internal diameter. Don't forget, we are keeping helium. In this case, we obtain two results through direct translation. In this case, we increase the speed by a factor 1.55, or we apply the speed translation, and in this case, we increase a little bit more the speed by a factor 1.86. This is a chromatogram relative to those two experiments. The first one, a runtime above 30 minutes. The second one, with helium, step 1, direct translation, a chromatogram with a runtime less than 23 minutes. Then, if you compare with second experiment where the speed increase, the runtime is less than 19 minutes. Don't forget, we are at this time only with helium as a carrier gas. Let's have a look at a zoom of 8 peak for the same section of step 1 and 2, and if we take care about the resolution between the 246 and the 245 trichlorophenol, it's quite the same, whatever the experiment consider. For instance, with the step 2, by applying the fast transfer, we win closely a factor 2, don't forget 1.86, and on the same time the resolution was reduced by a factor of only 3%. So it means that even in this case the speed transfer is very interesting. The following synoptic shows the effective translation of helium toward hydrogen in direct translation and in speed translation, using, as in the previous experiment, a shorter column with a smaller diameter. With direct translation, the runtime is decreased by a factor 2.59 while maintaining the resolution, while with a speed translation, the runtime is reduced by a factor 3.12 at the expense of the resolution. Like any SAP science process, it is always a problem of compromise. This is a respective chromatogram based on the experiment. The first one with helium with a runtime more than 30 minutes. The second chromatogram with a translation, common translation. The runtime is less than 40 minutes. And with a speed translation, the runtime is less than 12 minutes. Is this small loss of resolution so dramatic? Not at all. If we look at the resolution between the two isomers of the TCP, we go from 1.66 to 1.55 between our conventional method and the fast method with hydrogen. That is to say, a decrease of 7% regarding the resolution, while we have reduced the runtime by a factor close to 4. We can further reduce the chromatographic process by further reducing the size of the capillary column. The reference column is still the 30 meter RX 5 seal MS from Restec, while the shorter column has a length of 15 meters, an internal diameter of 0.15 millimeters, and a fast thickness of 0.15 micrometer. The result through the direct translation induce a speed increase by a factor of 3.67, while with a speed translation, the speed increase by a factor 4.35. This is the respective chromatogram, very nice, and with the latest experiment, we can easily see that the resolution is maintained. But we have to prove it. For instance, with the reference method, the resolution between the two trichlorophenol isomer 2.5 and 2.6 is 1.66, while with the high-speed GCMS with a shorter colon, the resolution is 1.51. It means we reduce the runtime by a factor of 0.35, and on the same time, always the story of compromise, we reduce the resolution only by a factor of 8%. But don't forget that even if the resolution is reduced between 2 or more peaks, you can play with the power of the mass spectrometer. Here are some more examples of chromatographic resolution, and even if for some compound like the dinitrobenzene and dimethyl phthalate this resolution can be affected, it is improved in fast GC between the 4-methylphenol and nitrosopropylamine. Even when working at higher pressure and with faster temperature ramp, the EPC works perfectly well, maintaining excellent retention time accuracy. Whatever the gas considered and the methodology considered, conventional or fast GCMS, the precision is above 5%. The fast GCMS imply narrower peaks, which should lead to apply a higher frequency for the acquisition in order to obtain enough points to define properly the chromatographic peak, and of course to obtain the purest mass spectrum. From my point of view, the right answer is time of flight mass spectrometry. The time of flight MS allows fast data acquisition speed, a full mass range, unskewed data is collected at all acquisition rate, and finally, these two features combined are ideal for deconvoluting fast GC data in complex samples. Above all, while using hydrogen, it is really interesting to use the stay clean open ion source design. Some urban legends in some laboratories tell us that hydrogen can affect negatively the quality of the mass spectrum and thus reduce the quality of the spectral recognition. This is just a legend. Here are the results for the 2,4,6 trichlorophenol, and we can see easily that the matching factors are identical, whatever the carrier gas considered. We obtain the same good results for another kind of compound, in this case the methyl naphthalene. And whatever the compound considered in your mixture, because I remember there were 72 different compounds, as you can see on this table, the matching factors are quite the same, whatever the compound considered. Keep on memory, we obtain a very similar spectral fragmentation. If we talk a while about sensitivity and quantification, we have established calibration curve for all compounds, obtain excellent linearity over 5 orders of magnitude, and this is very important. And you can see on the table that hydrogen does not bring any additional background. Indeed, the signal-to-noise ratio of a very low concentration injected, 1 picogram on colon, is very similar, whatever the carrier gas considered, helium or hydrogen. Unlike with other technology, we do not see any significant effect on sensitivity. This is some example of calibration curve from 1 ppb to 1000 ppb. helium is compared with hydrogen uses the same column and direct method transfer translation. As you can see previously, R square value were highly found to be similar. But the goal of this technique is not to play with standard, but to work on real sample. During this month of study, we work on drinking water, river water, and wastewater as well. You can see the chromatogram from a liquid-liquid micro extraction with hexane, and then 2 microliter injected in spitless mode. The silicone peaks you see on all chromatogram do not come from the colon phase, but unfortunately, they come from a pollution on the river. If we consider wastewater, several hundreds of peaks are eluted from the colon in less than 9 minutes. There is always coalition in a very high matrix loaded sample. And in this case, a tough MS acquisition speed with full mass range unskewed data allows deconvolution to work successfully. This is wastewater deconvolution example. In this case, the galax solid, the alkyl benzene and the siloxane eluted on the same time. So you have the caliper average spectrum on the top, and thanks to the deconvolution software, on the left middle you have the spectrum of the alkyl benzene, and on the right middle you have the deconvoluted spectrum of the galax solid. At the bottom you have the library batch. We are very good. So whatever the matrix configure, even if you have hundreds of peaks, even if you have a dramatic coalition, thanks to the high frequency and to the deconvolution software, it's possible to properly identify the compound and, of course, to perform the right quantification. In this case, in one of the wastewater, we quantify the exact beta-DN at 2.5 nanogram per liter, the methyl naphthalene at 1915 nanogram per liter, and the phenanthrene at 715 nanogram per liter. Look at the X scale. Don't forget that all those compounds elute within 9 minutes. So, my conclusion will be the following. Transfer to fast GC using hydrogen carrier gas can be made on an easy way. We talk about the safety consideration for working with hydrogen, so don't worry. The cost saving can be achieved by switching from helium to hydrogen over a short medium-term period, I think between 12 to 18 months. The chromatographic method transfer process can be managed nicely by following a systematic calculation approach, mainly based on the EasyGC freeware from Restec. Analysis throughput can be achieved significantly via reducing runtime whilst keeping excellent chromatographic resolution. And finally, using the suitable instrumentation is important, especially for obtaining good sensitivity, robust, high-quality MS data, and of course, comparable MS spectral fragmentation for identification purposes. In this case, we play with a tough MS and an open ion source design. It's time to finish, and I wish to thank all the project collaboration partners, LICO Europe and his application and technical teams through Nick Jones, Sebastiano Panto, Tomal Kovalchuk, and Jogan Wendt, Restec Corporation through Yap Dezou and Hans-Jörg Meyer, and the French gas generator company, FDGS, for the help, Jean-Marie Casanova, and Guillaume Agros. Thank you very much for your attention.
Excuse me. Frog in my throat before we even begin. Thanks, gentlemen, for your presentations. Great to see all those views on Fast GC, particularly there at the end, David, with your tricky real-world samples of wastewater. We've now got some time for some questions from our audience. So a reminder to the audience, here we have Tony, David, Franz, and Ed is there, really, honestly. We haven't fabricated his voice. It's just we can't get him on the video right now. But these guys are all on the all online to answer your questions. So feel free to send those in. We'll kick off. Shall we kick off with a tricky one? we've heard a lot about the benefits. We've heard a few of the cons from David, but someone asks, and I'll start this with you, Tony, because you kicked us off. What do you see as being the biggest challenges associated with the use of Fast GC?
Fast GC, as I've highlighted, is an incredible technique, but unfortunately it highlights any minor discrepancies that we have within the system. So like all forms of ultra fast performance, whether it be a fast car or whether it be fast chromatography, connectors and the small little things that perhaps on a bigger scale we're not so concerned with have a much bigger impact. Dispersion is a big issue. So we need to, as I say, make sure that the connectors are suitable. Hotspots as well. We need to make sure that there is even heating throughout that column oven. If we look beyond that, then sample loading is obviously an issue which I discussed in the earlier presentation. And we need to be very careful about the use of split ratios to make sure that we're not piling on as much on the column. The very quick analysis times then present challenges with the detector. So there's a raft of different challenges out there, but the benefits are massive in terms of that speed of analysis, sensitivity gains, etc. Thank you.
Thanks, Tony. Does anyone else have any additional comments? David, do you have any comments on the downside to Fast GC, if there are any, in your opinion?
I think one of the major things it would be based on the technical aspect. You should take care about, for instance, your EPC, because in this case you have to use a very high pressure above 150 psi. And for instance, we might take the high-speed GCMS for more than 20 years now, when the first PC arrived on the market, and very rapidly we were facing a lot of data. For instance, on one GC it was possible to obtain, for instance, 10 to 15 results per day with 90 to 95 minutes per run, and 1 or 2 years after the end of the development, we were facing around maybe 100 to 200 data per day for only one single GC.
Yeah, that's the challenge we've not mentioned, the sheer acquisition of data that starts to boggle minds at some point. Thank you very much. Let's have another question. Someone asks here. This is directed at you, Franz, but I'm sure other people can jump in. And I think you did share some of this, but maybe you can just give us a brief overview. What requirements must the GC fulfill for Fast GC operation? Simply.
Yes, we have talked already all the parameters. Means heating is one, of course, task. That means the linear heating rate of the GC must be fast. So should be over the whole temperature range of the oven. That means up to 400 degrees at least. So 30 degrees Celsius per minute should be the linear heating rate over the whole range. But then reverse, also we have to talk about the cooling speed. Means if you can rapidly heat, but then it cools very slowly from high temperatures to the low temperatures, then you lose, of course, let's say the runtime for the complete GC run is not short, only the chromatic runtime. That means you need a fast cooling speed. There's, of course, a restriction from the columns. So polar columns do not like very often too fast cooling. That means this must be then maybe restricted. Then, of course, we all go for the small inner diameter columns for very ultra fast GC. That means we have to operate with high pressures. That means the GC should be really able, let's say, to make pressures higher than 700 kilopascal. So that is so typically even with hydrogen as a 0.1 millimeter, so at 360 degrees, that is so roughly also with hydrogen than the possible pressure. Yeah, and then what I told, finally, we get very sharp peaks. We need a fast responding detection system. Thanks.
Thanks, Franz. Anyone else want to add anything to that question in terms of what one needs?
Rich, if I could just add and just comment on, Franz is exactly right. It's not just about a single component. It's about all of the components and making sure that they're mixed together. I already alluded to some of the challenges associated with Fast GC, And you can't address all of those challenges without a joined up thinking approach to it. So absolutely, Franz is absolutely right. It's about the instrumentation, it's about the column, it's about the detector, and having everything thought about in terms of that incredibly fast analysis.
Thanks very much, Tony. Here's a question that I think we've somewhat answered, and it's you know, maybe overtly obvious after the presentation, but I'm going to ask it anyway in case anyone's got any controversial opinions. But someone asks, what is the most suitable carrier gas associated with fast GC? Now there's a question. Tony, do you want to just kick us off on that one, that dangerous question, especially for Ed?
I think that if I was being controversial, I'd say something like nitrogen. But no, it's obviously hydrogen. You know, the faster diffusivity, the lower pressures that you get, the lower it absolutely has to be there I am slipping into nitrogen again. It has to be hydrogen. The disadvantages of hydrogen are that use of cylinders, it may not be ideal, particularly it's a particularly flammable gas, obviously, and there are dangers associated with that. But perhaps Ed has got a solution there that we could discuss.
Ed, do you want to jump in on that one? I'm sure the answer is hydrogen.
Yeah, I would tend to agree that it's hydrogen. And yeah, there are safer alternatives to cylinders available, of course, such as gas generators. So certainly I think that should be the approach that people take to be able to use the carrier gas safely.
Thanks, Ed. And while you're on, someone's asked.
But Rich, we have to break religion because we practice 10 years now. Of course, we banish cylinder for the gas room, from the gas room, and of course from the lab, and we play only with hydrogen gas generator. Okay, with the right system, with the right probe. Okay, you have to banish, for instance, the retention gap because you can promote leaks, you can banish graphite because you can promote leaks, but if you choose the right parts, there is no problem at all. You save time, and by the end, it's quite important also because the price of helium to increase. By the end, you save money, and it's for medium lab as well as for a big lab.
Thanks for that added comment, David. While we're on the topic of hydrogen, someone asks, and Ed, you may as well chip on this one as well. They say, how long would it take to convert from helium to hydrogen carrier gas? Which sounds a bit like a how long's a piece of string question, but nevertheless, can you give us a bit of a ballpark answer to that, Ed?
From GC side, sorry.
No, it's okay. I was going to say, first of all, it depends on how prepared you are, because obviously if you have not really considered all of the potential pitfalls and other factors that come into play, then that can end up costing you some time. And I think hopefully the other members of the panel would agree, but it will also depend on the detector type. So normally, if we're looking at FID detection, it should be simpler to make the transition than if we're looking at MS, for example, where there could be some hardware changes required and time for background to settle and so on. So it will also depend on how complex the mixture of analytes is. So it is a little bit how long is a piece of string, but it can be anything from a couple of hours to maybe a couple of days if you are waiting for a mass spec for the background to settle. I don't know if anyone else has any comments.
Franz, do you want to step in? I think you had something to say on
From
that.
the GC side, no problem. Just to connect on, let's say, the weir side or change the gas to these pneumatics. And if you use all the same parameters, just saying the GC now hydrogen is connected, then you can already start and you will get not identical but similar results. But what you see then with hydrogen, you can easily increase, and for example, only the linear velocity and you get definitely faster. So principally with hydrogen, you can achieve the same that you can achieve with helium or better.
Great, thanks, Franz. Here's a question that's just come in. Don't know who's best placed to take this one, but they say, what volatility range is usually covered? Anyone want to take that question?
Yeah, with helium, of course, you can, what I've shown, you can go also beyond this typical limits, which is given by the Van Deemter. But you see, with helium, the separation, the resolution decreases more faster if you go beyond, let's say, the 40 centimeters per second. That's much faster than with hydrogen. So with hydrogen, you lose less peak resolution if you increase even far above 100 centimeters per second. And of course, the second point is with helium, you have roughly more than double the pressure. And pressure is also, of course, also a point that finally influences your chromatography.
Thanks a lot, Franz. Here's another how long is a piece of string question, perhaps. But we did talk a little bit about not overloading columns. Someone asks, what amount of sample solution should one inject for a fast GC method? David, do you want to give us a bit of a range there?
Yes, I perform a lot of tests by the past in my lab. The maximum loaded was, for instance, for the 0.18 column was around 1 ppb. 1 pp on column. It was a maximum. If we think about complex matrix like a sludge or like a wastewater, of course we inject in a splitless mode, because in our case in an environmental lab we need a lot of sensitivity. So in this case we can around 1 ppb on column at the maximum.
Any additional comments from anyone on that question? No.
Yeah, concerning of course, normally you have to consider that you operate with higher split ratios, because you must also imagine on this, let's say, a smaller inner diameter columns. We talk here always about linear velocities, but the typical flow rate, the volume flow over the column goes down. And we live in a real world. We have an injection system that has a certain gas volume. That means the transfer on the column by the injection system is, of course, crucial. So typically with fast GC, we operate with higher, let's say, split ratios, so 1 to 40, only to have a good transfer on the column. And finally, we get still normally better detection limits because of the sharper peaks.
Thanks a lot, Franz. I think we've got time for one more question, so let's make it a technical one, or a future-facing one. Someone says, do you see any limitations in the reduction of the diameter of the capillary so that even faster chromatography can be achieved? Tony, you look like you're champing at the bit to take that one.
I am, because I think this is potentially one of the really exciting areas that we could move into. We've already seen some developments in the research field where people are looking at etching GC capillaries, and this has been around for some time. Yes, there are massive challenges. I've already hinted at what those challenges are with conventional fast GC. As we go down to smaller and smaller IDs, is there a limit? Yeah, at some point we're going to get to a point where we can't physically inject a reasonable amount of samples so that we can see it. But certainly I think that we should be looking at diameters of approaching 1 to 2 micron, and perhaps even in the nanometer range. I think that would be exciting technology, and research are already in that sort of realm. So I think there's a lot of opportunity to develop. It's then trying to transfer that technology into something that is going to be robust and suitable for most chromatography users. Therein lies the massive challenge. I think researchers across the world were looking at, yeah, we can do it, but can we mass produce it? I don't know. I think that's for the manufacturers to look at and try and come up with solutions. But I certainly think we should be looking at 1 to 2 microns as being something that is achievable in a not too distant future, from my opinion.
But what will David do with all of his data projects at that point? Do we need such speed? That's the question. Does anyone else want to take that question, or have they got any additional opinions on the limits of fast GC? How fast can we go? How narrow can we make the capillaries? Any more comments before I close? I'll take that muted panel as a no. I've just muted myself as well. Hooray! I'd just like to say we've reached the end of the panel. In fact, we've gone over. So I hope you're still with us. But I'd just like to thank our 4 experts for their not just for their presentations, but their contributions to the Q&A session, which was great. We do have some questions that we didn't get round to. I'll make sure I field those out to the relevant people and get you an answer. I'd like to offer a big thanks to our sponsors, Avantor, Leco, Peak Scientific, and Shimadzu. And finally, and by no means least, I'd like to thank everyone for listening. Thank you, and goodbye.
Bye-bye.
Goodbye. Thank you.
Goodbye. Thanks.
Goodbye.